Yo, welcome back. All right, here we go. We're going to talk about limit fundamentals and limit properties. We're going to start with the limit of a constant function, a lot of times referred to as how do you find the limit of a constant. So we're going to relate this back to what we have been doing, which is looking at limits graphically. So you'd want to start with, well, what does the graph of a constant function look like? So in other words, if I had the function f of x equals k, where k was some real number, right? K is an element of the set of reals. What's that going to look like? So hopefully you'd say a horizontal line, not a line, but a horizontal line, right? So this would be the graph of a constant function. Horizontal line, did my best there to draw it, right? So this is f of x equals k. Now I'm drawing it for k being positive, greater than 0, but I did not have to. I could draw it uh, below the x-axis if I wanted. So now let's look at a limit. So if I wanted to do the limit of some constant as x went to say some other value c, maybe c is right there, what's that going to be? So let's think about it. As my x values, right, as my x values go to c from the right side, what do the corresponding functional values approach? That little right-handed limit buggy, right? What unique y value is he getting close to? Likewise, as my x values get close to c from the left side, what are my corresponding functional values getting close to? Well, not only are they getting close to, if you think about it, they're really remaining steady at whatever this y value here is, whatever the constant is, right? They're just staying on that horizontal line. So the limit of k as x goes to c is just going to be k. So the way we remember that is that we say the limit of a constant is going to be the constant itself. So I'll move this magical little red box here. Make sure you write that down. Right? Left you a little line in your notes for you to write that down. The limit of a constant is in fact the constant itself. So not too earth-shattering exciting, especially when you see the graph, but let's do some cheese ball examples, right, where we throw actual numbers in. So if I wanted to do the limit of 5 as x went to 2, right, what would that be? Your only two real guesses are 2 or 5, right? But hopefully you're saying 5, right? The limit of 5 as x goes to 2 is 5. Again, if I was to look at the graph, this will be the last time I do this, right? I put 2 here and I graph 1, 2, 3, 4, 5. So I graph the constant y equals 5 here, right? So this would be like f of x equals 5, right? As my x values go to 2 from the left, my corresponding y values are approaching 5. So x goes to 2 from the right, my corresponding functional values are approaching, in fact, really remaining steady at 5. Again, the limit of a constant is the constant itself. And we can try and make this look as complicated as possible, but it's really not. So if I had the limit of, say, negative 1/2 as x went to 6 from the right side, nothing changes, right? Just because it's a one-sided limit, right? If I'm just coming in from one side, I'm still going to be on that constant. So that doesn't change anything. The value that I'm approaching, the c value, that means nothing. It's all about what the constant is. And here's an example of a negative constant. So that would be like when the horizontal line was below the x-axis. All right, so no big deal there, right? One that maybe might throw you for a loop, maybe it won't, is what if I had the limit of, again, I'll just make a number up. Maybe I'll say pi, right? So a cool constant, right? Pi is just a number. And now I say as x goes to maybe infinity, right? So what's that going to be? Well, again, the limit of a constant is the constant itself. So even if you're going to infinity, if your inputs are going this way forever, your corresponding functional values are going to be on whatever that constant is. All right, so limit of a constant, constant itself, no big deal, no great shakes there. All right, so let's take a look at this guy now. Limit of an identity function. Well, first off, you got to know what the identity function is, and most of you probably know what it is, although you might not know that it's called the identity function. And it's just the function f of x equals x. You can think about why that makes sense. If your input is x, that's what your output's equal to, so it keeps its identity, hence the name identity function. So again, let's go back to what we know best. Let's graph f of x equals x, otherwise known as y equals x, right? That's going to be a line that has a slope of 1 and a y-intercept of 0. Okay? And if I wanted to look at this now, again, maybe the limit of x as x goes to some value c, what would that be? Well, let me chuck c on here. Right now, think about this for a second. This is the identity function. So if my input x here, if my input is c, Well, then that would mean the output right here, the y value, also has to be c, right? Because it's f of x equals x. So think about what that means now when you do a limit, and I'll show both sides. If my x values go to c from the right, my corresponding functional values are approaching that unique limiting y value of c, the red c, right? And no pun intended on that. As my x values go to c from the left, the corresponding functional values, right, are approaching, again, this y value of c. So the answer is just going to be c. So the limit of x as x goes to c, makes sense when you think about it out loud, is just going to be c. Some teachers refer to that as you're just substituting the c in for x, and you actually can refer to it that way, and we'll get more into that as we do some more limit problems. So again, let's just look at some cheese ball examples that drive this home. If I have the limit of x as x goes to 10, that's just going to be 10, right? You can graph it out and see if you want. If I wanted to get fancy schmancy and say, hey, what's the limit of x as x goes to -1, maybe from the left? Well, again, it doesn't matter if I'm coming from the left or from the right. That input's the same as the output. I'm going to be approaching that value that I'm approaching, which in this case, the x would be -1, right? But also the y value at that point would be -1. All right, and then maybe we'll do one last one. What would the limit of x be as x goes to infinity? Well, if you think about this is your graph of y equals x here. As x goes to infinity, that way forever, the graph's going to go up forever. So we say it goes off towards positive infinity, right? The y value keeps getting bigger and bigger and bigger. And that is a descriptive way of saying does not exist. Not only does it exist, but we're going to tell you it goes to positive infinity, right? So that's the limit of an identity function. So nothing too crazy about that, but it turns out that all of or most of the limit problems we do, they kind of go back to these roots here, that the limit of a constant is a constant itself, and the limit of an identity function is done in this manner. But there is a couple other things we want to add to that, and these are some basic limit properties. And I'm not going to prove these properties to you. I'm just going to kind of shoot through them, which is not the norm for this class, but I'm just going to choose to do it for these particular problems. So here we go. So how do you read this? This is read the limit of f of x plus g of x as x goes to a. Turns out that if you wanted to do this, you can do the limit of each function individually. So first do the limit of f of x as x goes to a, then do the limit of g of x as x goes to a, and then you know what to do with those two answers. Hopefully you say add them, right? And so the way we remember this is we say that the limit of a sum is in fact the sum of the limits, right? So I'm missing the quotation mark there. So you should write this down. The limit of a sum is the sum of the limits. On your notes, I gave you a little nice little horizontal line. You're writing this down on that line. All right, and you can kind of look at it here. This is a sum. I'm adding two functions, f and g. So the limit of that sum is simply the sum of the two individual limits. Okay, so that's the limit sum property. Nothing too bananas about that. That's what it is. Take a look at this guy, right? Do you think anything crazy is going to change here? Hopefully you said no. Well, what if I wanted to do the limit of a difference? Well, again, what you can do is you can do the limit of each function individually, right? So first do the limit of f of x, then do the limit of g of x, and then go ahead and do whatever that operation is, which in this case is minus. And so if you had to guess what would the sentence be that you write for this guy? Hopefully you would say the limit of a difference is the difference of the limits, right? I don't want you to say things like you're distributing the limit, right? We're not doing multiplication here. This is read the limit of a difference, and it turns out that it's evaluating by doing the difference of the individual limits, okay? Now, I drew this up or gave you an example here of just two functions, f and g, but it can expand to more than two functions. So if I was adding three functions together, I'd still have the limit of a sum, and to do that, it'd be the sum of the limits. I would just find the limit of each one individually and then add them up. So understand that it does expand to more than two functions. You're going to hear me a lot of times say that limits behave nicely, all right? And that is because where I have these capital words here, you can almost replace that with any binary operation, right? So limit of sum of the limits, limit of difference of the limits, put anything you want in for those words that are capitalized, and it's still probably going to be true. So take a look at what I mean. So what is this? If you had to look at that, right? What would you think that would be? Hopefully you would say that's the limit of a product, right? Because you have f of x times g of x. You don't actually see a multiplication symbol, but that's multiplication by juxtaposition, right? You put two things next to each other. All right, for the purpose of analysis, in this case, you're multiplying. So that's the limit of a product. Well, guess what? That's going to be the product of the limits, right? So now how do I write that? How would I expand that? Because this is what I'm going to be interested in. Well, again, think about or listen to how I say this. You do the limit of each individual function, limit of f, limit of g, and then you do the operation, which in this case is product. So you multiply it. So the limit of a product is the product of the limits, right? Probably already know what I'm going to say here, right? This is the limit of a quotient, right? I'm dividing two functions. Well, guess what? Do the limit of each individual function separately, and then guess what you're going to do? You're going to go ahead and you're going to divide those two functions. So the limit of a quotient is the quotient of the limits. Now, this one has a little bit of a catch, right? We got to do a little whoop, comma, and we got to say this. Provided that, this is true, provided that the limit of g of x as x goes to a is not equal to, do you know what I'm going to say? 0, right? Because then you'd have division by 0, and nobody in the math world likes division by 0. All right, so again, if I'm looking at this, this is the limit of a quotient is the quotient of limits, right? So notice limit of sum of the limits, limit of a difference of the limits, limit of a product of the limits, limit of a quotient of the limits. That's what I mean when I say limits behave nicely with these operations that we have. All right, next two are cool. Maybe a little weird, but same type of idea. So now what is this? This is the limit of a constant k times a function. So I really want to view that as a constant times a function. But you might say, hey, hang on a second. That's a product, right? K times f of x. And you just showed me that the limit of a product is the product of the limit. So I can rewrite this as the limit of k as x goes to a times the limit of f of x as x goes to a. And you're like, well, wait a minute. We started this session off with finding out that the limit of a constant is just a constant itself, right? So this would just be k, it would simplify to that. And so this is what I get. And so now I showed some work here, and let me just kind of write this horizontally here. So I have the limit of k times f of x as x goes to a. It turns out when we did it, it's just k times the limit of f of x as x goes to a. And the way we remember this is we say that a constant can be moved through a limit. So here is a constant times a function. And if you think about it, I'm kind of like moving it through the limit. And now here's the constant outside limit. You're not really doing that. You're kind of applying these two properties. But my point is you don't want to view this as a product. So in other words, and this is going to be true when we do some other things later in the course, when one of your factors is a constant, then view that, see that as a constant times a function as opposed to a product of two functions, right? Because when it's a constant times a function, we can just pull the constant out. You do that in one step. There's no need to show the step that I showed there, okay? So again, the way I would say that simply is that a constant can be moved through a limit. All right, the last one we got here, we have a function raised to a power. It looks like a fractional power. All right, so I have the limit. We can view this, and this is a little weird. We can view this as the limit of a power, and guess what? That's the power of the limit. Now that one I'll give you. That's a little wacky to think about to say that. So let's just kind of do what we've been doing, which is do the limit of just the function by itself with nothing else, right? And then go ahead and then apply, in this case, raise that whole answer to the power. And that's what we mean. We say the limit of a power is the power of the limit. Okay, so you do the limit of the innermost function and just apply the power to it. Now, what's neat here, I'm going to give a little example with this, is this actually would lead itself to doing a problem like this. Maybe I do the limit as x goes to c of radical f of x. How could I rewrite that? Well, I could rewrite that as, again, watch what I do here. Do the limit of the function without whatever the operation is. So just do the limit of fx, x goes to c, ignore the radical, and then do the radical of the limit. So you can view this as the limit of a radical is the radical of the limit, and that would be true and that works. So you're like, why are you showing me that on line 6? Well, because hopefully you remember that if you have something like radical f of x, that radicals can be rewritten, right, using fractional powers, in this case, f of x to the half. So it would apply there, okay? So those are some limit properties and fundamentals. I'm going to have another video doing some examples, and they're going to get us going. So see you soon.